Thank you very much, and thank you for the introduction. And I want to thank the organizers for giving me the opportunity to give a presentation in this workshop. And again, I am sorry for not being able to be there in person with you in Vienna now. So I will give you an overview of some of my recent research results in which we have investigated the problem of quantifying uncertainty in nonlinear plasma physics problems. And this is more a talk on the application side of things. And we have used adaptive sparse grids for this purpose. And by the end of this talk, I will hopefully convey to you the idea that adaptive sparse grids can be an effective tool in nonlinear plasma physics problems for quantifying uncertainty. And in the direction that was mentioned a few minutes ago, I will also mention some of potential research directions that can be maybe done with in collaboration with some of you in the room. So hopefully, we can have a short discussion at the end or on Wednesday on this theme. And I want to acknowledge my collaborators on this work, on this research, which was done with a postdoc from the Oden Institute at UT Austin, Gabriele Merlo, and with one of my two postdoc mentors here at the Oden Institute, Frank Jenko, who is at the Max Planck Institute for Plasma Physics in Garching, but also affiliated with the Oden Institute in Austin. And the motivation for this kind of work and the motivation for my research in this direction done with Frank, who is a computational plasma physicist, is basically to try to aid the understanding of fusion plasmas via numerical simulations. And why fusion plasmas are important? Well, we live in a world in which the demand for energy increases year by year. And a report done in around 2009 projects that by the year 2100, the energy needs of humanities will increase tremendously by almost a factor of 5 compared to today. And these energy needs cannot be really sustained by the current energy sources that we employ in the world. And of course, to this end, we will need new energy sources, which ideally are very effective, very efficient, and for the sake of this planet, hopefully will also be green energy sources. And one such a potential energy source, which is one of the prominent research fields in physics nowadays, is the idea of trying to replicate here on Earth the process that fuels stars, such as the sun. And this is the so-called process of fusion. And the reaction that we try to replicate here on Earth is the one that can be achieved in a laboratory setting, which is the deuterium-tritium fusion reaction, which is depicted on the right of this slide, in which basically the two isotopes of hydrogen can fuse together, form a heavier element, such as helium, which is unstable, which then decays. And then when this happens, there is a loss of mass, which is transformed into energy via the famous Einstein's equation E equals mc squared. And this loss of mass, which is transformed into energy, then will be used with the end goal for electricity production. Of course, if we try to compress something as big as the sun here on Earth in a device that will measure a few tens of meters in diameter, is very, very challenging. And to do that, basically, we need to increase the temperature that is in the core of the sun by roughly a factor of 10. So the temperature in the core of the sun is roughly 15 million Kelvin. To achieve this on Earth, we need to make this up to 100 million, 150 million degrees to obtain the fusion reaction, which basically creates a plasma. And you can think of a plasma as a very hot and ionized gas containing ions and electrons. Of course, we cannot really hold these types of temperatures in a device here on Earth, in any type of device, because no existing material can hold these temperatures. So around the 1960s, physicists came up with the idea that, okay, we cannot do this, but we can take advantage of the fact that the plasma consists of charged particles. Then we can keep these charged particles inside the magnetic field, so we confine them. And then basically, if we introduce a magnetic field, then the charged particles will follow the magnetic field lines. In order to avoid having losses at the end, basically we need to have a closed loop, a closed system, which is, in this case, a helically twisted field lines around the torus. And such a design, in which we have a helically twisted field line around the torus, which is closed, is called the tokamak design. This is depicted here on the right of the slide. And here basically you see the device, which is surrounded by coils, which are used to generate the electric and magnetic fields needed to hold the plasma. And such a device is currently, there are several around the world used for academic purposes, but one of them that wants to sort of prove this principle at a scale that can be then transferred in the next step to energy production is this ITER project, which is currently under construction in the south of France. This is an international collaborators. And the goal of ITER is to ideally obtain 500 megawatt of fusion power, thus proving that plasma fusion can be a way towards new energy sources. And to give you a sort of sense of scale of ITER, basically, which is depicted here on the left, the diameter of the tokamak will be around 30 meters. So it will be quite a large device. And this is the current site where ITER is being under construction. This picture was taken a few years ago. And basically, it will be hosted into this big building in the center. Now, one of the main goals of plasma physics simulations is to do simulations for devices such as ITER. However, in terms of computational simulations, we are not there yet, because simulating a device such as ITER is beyond the capabilities of current codes, simulation codes and supercomputers. And actually, this is one of the main targets for the upcoming exascale computers. And that will offer us the opportunity to try to do uncertainty quantification for such a problem, which is of practical relevance. We are not there yet. However, we can still do complex plasma physics simulations that are practically relevant. And I will talk to you in a minute about this. But basically, as I said, fusion, the idea of fusion is around for a long time. And then the one question that pops up very frequently is, why is fusion so difficult to achieve in the laboratory? Because we still haven't achieved it yet. Well, it turns out to be a very, very complex process, because in order to achieve fusion, which again happens at millions of degrees Kelvin, we need to have a self-heating energy source that must compensate for energy losses, which can come from, for example, electromagnetic radiation, and even more important and problematic is the turbulent transport. And basically, what we want to do is we want to ensure that the plasma stays in the center, in the core of the device. So we need to ensure that we have large central pressure. And we also need to ensure, which is what prevents for the moment in the laboratory, a large energy confinement time. So because basically the reaction needs to happen for sufficiently long such that it becomes self-sustained. And this is where we are not there yet. If you look on this picture here in the center, I see that the x-axis is shifted to the left. Basically, we want to reach this region here in the upper part where ITER will be, where around 150 million degrees Kelvin inside in the core, where hopefully we'll be close to ignition. And basically what the key element that prevents this from happening is the turbulent transport that forms. And this turbulent transport starts forming in the core, from the core, and then radiates towards the outside part of the tokamak. And here you see, for example, an experiment done at Aztecs where you can see the fluctuations in plasma temperature and density that happen at a microscale. And therefore, quantifying, predicting, and controlling this turbulent transport is key to designing optimized fusion power plants. Now, as I said, we are not necessarily there yet in terms of simulating ITER, but we can still do something useful in terms of trying to quantify uncertainty in these simulations. And for the purpose of this presentation, and for the purpose of our research that I'm going to present to you next, we are focusing on turbulent transport in the edge of fusion reactors. And basically what happens is that So if we go again to the tokamak design, we have it here on the left. We take a cross-section of that, and then we analyze what happens there, and we see that turbulent fluctuations, which are driven by microinstabilities, so basically turbulence that forms at the sub-millimeter scale, cause heat losses that radiate from the hot core towards the colder edge, which we want to avoid, because this is what prevents basically the reaction to self-sustain. And what happens is that in so-called high confinement mode discharges, which basically happen in the outer edge of fusion devices, which is depicted on the third plot from the left, a region which is called the pedestal forms that is characterized by reduced transport, which is good, but also steep gradients. And by gradients, I mean temperature and density gradients. And the properties of this pedestal are influenced by the residual turbulent transport. And as it turns out, quantifying the impact of this turbulent transport is essential for setting the overall performance of these devices. So doing these types of simulations are very relevant for the purpose of optimizing the performance of fusion devices. And as you can see here in the last plot on the right, turbulence that forms in this region, basically this is at the microscale level. So we see that turbulence forms at a very, very small scale. This is problematic, of course. And for our purposes, why is uncertainty quantification and sensitivity analysis necessary here? Is because these simulations generally begin from experimental values for things such as density and temperature, which are generally characterized by large experimental error bars, simply because the experimental data is characterized by a lot of uncertainty, and also other parameters such as the ones that, for example, characterize the magnetic geometry, or other parameters are also affected by uncertainty, and it is important to understand the influence of these parameters. So basically, this creates the motivation for this work, which is try to do higher dimensional uncertainty quantification at scale, simply because these types of simulations tend to be computationally quite expensive. And to give you first a pictorial depiction of this, so here we are interested in the task of uncertainty quantification, and by that I mean uncertainty propagation and sensitivity analysis, which is relevant for plasma physics simulations, where basically we want to do this in a black box or non-intrusive way, meaning that we put an outer loop around the high fidelity model, which is a simulation code that we trust to give us the right answer. This model depends on certain inputs, and for each uncertain input, we compute an output of interest, and then we collect an ensemble of these, and then we do something useful with them. And of course, when these simulations are nonlinear plasma fusion simulations, they tend to be computationally expensive, so that we cannot really afford to do a large ensemble of these simulations, simply because it becomes computationally prohibitive. Then the question is, how do we address this and still be able to do uncertainty quantification? And here is a slide summarizing some of the modern methods for high dimensional UQ. Unfortunately, I cannot really do justice to all of them, so I apologize for the references that I have forgot about. And of course, most of these developments have been done with by people that are currently in the room or their collaborators. And I want to mention sparse approximations, which are a method suitable for high dimensional UQ with adaptivity, or if it's done on a grid, the sparse grid approximation. That includes a large body of work. I also want to mention multi-level, multi-index, and multi-fidelity methods, which are specially designed to address computationally expensive problems. And I think there is a lot of potential here for applying something like multi-level methods, and I'll mention this at the end. I also want to mention quasi-Monte Carlo methods, which are great quadrature methods for higher dimensional problems. And recently, a lot of interest went into the idea of using machine learning of deep networks for higher dimensional problems and for creating surrogate models. And also a lot of tremendous progress was done into understanding these methods theoretically better. And of course, others. And for the purpose of this presentation, what I will focus on will be on dimension-adaptive sparse grids for tackling these complex nonlinear plasma physics problems. And basically, what's the idea here is that these problems and problems that try to simulate the real world generally have structure. In the sense that if we are given a problem with the uncertain inputs, what happens is that generally we have a lower number of inputs that are important, so the dimensionality is lower, the intrinsic dimensionality. And also the parameters that tend to be important tend to be anisotropically coupled. And then the question is, how can we exploit this structure efficiently such that we decrease the effort that we invest into performing the uncertainty quantification task? And one way is, for example, to do a set of simulations and then try to learn this via something like local sensitivity analysis or other types of sensitivity analysis, which we don't want to do because, again, these simulations tend to be very expensive. And here what we want is to learn this structure online via adaptive refinement, which is sort of the best compromise that we could do for the moment. Adaptive refinement is driven by a refinement indicator, which dictates how the refinement process performed, and this refinement indicator is crucial to perform the adaptivity efficiently. And of course, for the purpose of plasma physics, we want to keep the number of simulations as small as possible, simply because we have a significant computational cost per simulation, but also the human cost is actually quite significant here, because this simulation can sometimes require a few days of our lives to be performed. But that means we start the simulation, and then the first few iterations end. We need to make sure that they are sufficiently well resolved, the turbulent scale that we're interested in is sufficiently well resolved. We continue the simulation, then we can do this for days and days. So it can be quite cumbersome to do a study in which even 50 simulations are performed, because this can take even months. And ideally, we want to avoid this. So we want to keep the number of simulations as small as possible. So basically, to get a bit into more detail, so the problem formulation here is that we are given a high fidelity model, so a simulation code that we trust to give us the right answer, and let's call this FH, that depends on certain inputs. So this high fidelity model here is, let's say, the plasma physics simulation code. The uncertain inputs parameterize this model, and these are, let's say, continuous random variables defined on a suitably chosen probability space that are distributed according to a density pi. In the context of plasma physics, these parameters can be, for example, the particle species, temperatures, or densities. And what we want to do is compute outputs of interest, which here can be, for example, heat fluxes or particle fluxes. And then from these outputs of interest, we want to compute things such as expectation, variance, so standard moments for done in uncertainty propagation, and also sensitivity indices, because this sensitivity information is actually very important for physicists here. And for simplicity, because I use sparse approximations here, I assume that the certain inputs are independent. So the vector of uncertain inputs has an independent component, which means basically that the input density has a product structure. And then basically, as I said, we based our approximation on sparse grids. And to give you an overview, sparse grid approximations are basically multivariate approximations based on cleverly chosen 1D tensorizations. So basically, a sparse grid approximation can be written as a linear combination of surpluses that are obtained by tensorizing one-dimensional differences in all the directions. So we start from one-dimensional approximations, and then we lift those to the dimensions via tensorization. And basically, to define the sparse grid approximation, we need three ingredients. The first one is to specify the one-dimensional approximations on which these d-dimensional approximations are constructed. In our case, we use interpolation, but also other approximations can be used, for example, spectral projection, or also known as polynomial chaos expansions in the context of UQ. We need to define a point sequence to construct the one-dimensional approximations. And in our case, we chose to use layup points simply because we wanted a setup that ideally led to the least number of possible simulations that we can perform. So we wanted to be as greedy as possible. And layup points are arbitrarily granular, which we like because that means that they increase very slow with the level in the sparse grid approximation. So we don't end up with a large number of points at high levels if needed to go there. And also it was shown, for example, in this work that they provide accurate interpolation approximations. For the uniform density, for example, layout points are constructed as shown here, where the first point is chosen arbitrarily inside the input domain. So here I chose it at the middle at 0, and then the remaining points are constructed greedily by doing this non-convex optimization problem. And of course, the last and most important ingredient here is the multi-index set, which basically sets up the way this the combination of surpluses is done. And the multi-index needs to be downward closed in a sparse-width approximation to basically ensure that all 1D differences in the multivariate approximation can be computed. And its cardinality is crucial for the efficiency of the approximation, because the bigger this multi-index set is, then the more points we have in the sparse read, and then the more simulations we need to do. So we want to keep its cardinality as low as possible. If we were to do a static choice of the multi-index set, which is typically done with respect to the one norm, so it's something like a simplex in D dimensions, this drastically reduces the number of points compared to a full grid approach, but still it might be very expensive for our purposes if we work in relatively high dimensions. By that, I mean that I'm talking about simulations in which it makes a big difference if we can avoid doing, for example, 100 simulations and we do only 50. That can make a big difference. So our approach then is to construct this multi-index set adaptively. And for that, we used Dimension-adaptivity, which was developed about 20 years ago by Ionut-Gabriel and then independently by Marcus, where basically the multi-index set is split into two sets. The so-called old index set O, which contains the set of already visited multi-indices and the subspaces associated with these multi-indices, and the active set, which contains the multi-indices that can be refined. And the refinement process is done with respect to a refinement indicator, which typically is a function that depends on the norm of the surpluses associated with the active set. And what happens is that at each refinement step, we select the multi-index with the largest indicator. That is a heuristic for saying that this multi-index needs to be refined. And then we move the multi-index with the largest indicator to the old index set. And then we add the refinement process basically means that we add all admissible forward neighbors to A. So all the forward neighbors, they keep the multi-index set downward closed. And simple depiction here in the bottom of the slides, basically 3 refinement steps in which we see that the multi-index with the largest refinement indicator gets refined. And we see in this picture sort of indicates that we have a 2D problem in which the second direction is more important than the first. So the multi-index set tries to emulate this structure. And what we want to do is we want to define a refinement indicator that exploits stochastic information about the uncertain inputs such that we can perform the refinement process with respect to this information. So what we do is that we want to obtain basically from the norm of the surpluses, we want to obtain stochastic information. And to this end, to make things easier computationally, we recourse to a spectral basis. And if we use interpolation as the main operation, we need to do a mapping or transformation to a spectral basis to obtain a spectral projection. And this, for example, was done also previously in this work from which I drew the inspiration from. And why is that? Because if I have a spectral basis and I take the square delta norm of the surpluses, I obtain a decomposition that contains a contribution to the mean, which is generally small, and the contribution to the variance of the respective subspace. And what we do further is that we decompose this variance using a Sobol decomposition, which again was shown to be equivalent to a spectral projection decomposition, in which I obtain information about the individual contributions of each of the D parameters, contributions due to interactions between 2 parameters, between 3 parameters, and so forth, up to the interaction between all D parameters. And basically, these variance surpluses here are nothing else but unnormalized Sobol indices. And then having this information available, what we do next is we compare each term in the decomposition above with a user-defined tolerance, which serves as a heuristic for with the accuracy with which we want the algorithm to explore the specific direction. Then we count how many of these tolerances are exceeded. And from this, we compute a so-called sensitivity score, which serves as our refinement indicator. So basically, the refinement indicator that we use here is the one that is based on stochastic information about the uncertain inputs in each subspace for refinement. And then we continue the refinement process until neither of these tolerances are exceeded, which is, again, a heuristic that tells us that we don't need to explore any of the individual directions or interactions further. And to give you a sort of a brief visual summary of the approach, so let's say that we are in the middle of the refinement process. We have a problem for visualization purposes with 3 inputs. So I am given 7 tolerances, so 3 for the individual inputs and then the rest for all possible interactions. We compute the sensitivity scores. And then if we decide that the refinement process needs to continue, meaning that these tolerances have not been reached, then what we do is that we refine the multi-index with the largest refinement indicator. We add its forward neighbors. And then basically these forward neighbors will contain the points that will enrich the sparse grid, which is shown here in the upper left. In this case, we have 3 new points added. If I have 3 new points added, because these are independent of each other, I can perform the respective simulations independently. And assuming that this large scale, then we'll perform them on a supercomputer. We take the simulation results, compute the output of interest, and then based on these, we compute again the sensitivity scores for the new subspaces, and then we decide whether do we continue the refinement process or not. If we stop it, then we can do post-processing and we compute something like moments of the output of interest, such as expectational variance. We can do sensitivity analysis. And even more, because the approach is based on interpolation, we also have a reduced model available, which can be used for other purposes. And now I want to show you the potential of these methods in a nonlinear plasma physics problem with 8 parameters that is concerned with turbulent transport in the edge of tokamaks, and hopefully convey to you the idea that these types of approaches have a great potential for these problems. And then at the end, I will mention some potential future directions in which we can improve on these results. So basically, again, we are interested in the problem of turbulent transport in the edge of fusion devices. And what happens here is that the turbulent transport is generally driven by changes in temperature gradient. And this is a so-called an electron temperature gradient-driven turbulence. This is the jargon that is used in plasma physics. To do the high-fidelity simulation, we use the gyrokinetic simulation code GENE, which is developed at the Max Planck Institute for Plasma Physics, which is one of the leading codes for numerical plasma fusion. GENE is a so-called gyrokinetic code, which self-consistently solves the Vlasov-Maxwell system of coupled interval differential equations in a 5D phase space. So basically, very briefly, CFD models are not accurate enough to capture the scales that are of interest in these problems. So physicists recourse to kinetic models. Kinetic models are defined in 6 dimensions, 3 positions, 3 velocities, but those are unfortunately computationally too expensive to be simulated even on very large supercomputers. So to this end, a theory called the gyrokinetic theory was developed some years ago, which reduces the dimension of the phase space from 6 to 5, where one of the velocity components basically is averaged out because that is not at the scale of interest. And in order to solve these equations, we need an equation that models the dynamics of the distribution function for each particle. And in this case, this is a gyrokinetic Vlasov equation. And because particles live in a magnetic and electric field, we also need equations for those. And in GENE, we solve 2 of the Maxwell equations, so the Poisson and the Ampere's equations for the fields. The setup that we have considered here required about 250 million degrees of freedom to be discretized in the 5D phase space, which is a relatively high number. And to perform these simulations, we have used 16 nodes on the Frontera supercomputer. And in single precision, they required an average of about 8,000 CPU hours. So on average, basically, I had to wait about 9 hours for such a simulation on 16 nodes or 900 cores. And we have a case that is based on a discharge from the D3D tokamak, which is one of the devices in the US that is used for academic research in plasma physics in San Diego. And basically, the physicists gave me a parameter set that comprised 8 uncertain inputs. So we had an 8-dimensional problem in which the inputs were modeled as independent, uniform random variables. To give you an idea about what would mean in this problem to use a full tensor grid with a mere 3 points per dimension. So that's 3 to 8 simulations in total. Here we'll have to do about 6,500 simulations, which doesn't necessarily sound like a large number, but in this case, if we were to perform these on this problem, not to mention that it will take probably a few months, even more, to perform, they will require also a budget of about 53 million core hours, which is too big. And the simulation output of interest in these types of problems, which is what really gave me hope that we can actually do UQ in such a problem, is that they are not interested in fields themselves, but rather they're interested in time averaged quantities. So generally in these simulations, we want to understand for example, the heat flux due to electron-driven turbulence. And the quantity of the output of interest is the time average value of this heat flux, which is a function of time. So basically the output of interest here is a scalar. And the 8 input parameters that were considered here were chosen such that they mimic a realistic setting. And we have considered the electron temperature and density, which are generally the parameters that are controlled in an experimental setting. We also have considered the gradients or inverse scale lengths, which gives 4 parameters. Since we wanted to be realistic here, we also have considered impurities and parameters that account for impurities, the next 2 parameters. And then the last 2 parameters are parameters associated with the magnetic geometry of this problem, which gave a total of 8. And to give you an idea about the experimental setting here, so the nominal temperature was about 0.4 kiloelectron volt, which basically means a heating power of roughly 5 million Kelvin here. So not quite at the level of ITER, but what is generally done in these devices for academic research. That's the typical temperature ranges, which is still pretty high. And basically, we have applied our dimension-adaptive approach for this 8-dimensional problem. And to my surprise, we ended up with a total cost of only 57 simulations. Still, it took me in total about a few months to perform because it's not necessarily straightforward to perform these simulations. But when I began this project, I didn't really know what to expect, to be honest. I didn't really expect it to work at all. But then to my surprise, while I was performing these simulations, after 57, I realized that I reached a tolerance of 10 to negative 4, which is sufficiently small for these purposes. 57 runs is not necessarily a really high cost for an 8-dimensional problem. And basically in the post-processing, the most important quantity for the physicist was the sensitivity analysis part. And this is very useful for them. And we have observed that out of the 8 parameters, only 2 are dominating, so only 2 are very important, which are the 2 gradients. And even more, we have observed, because we have the ability to compute sensitivity indices corresponding to interactions between parameters, that these gradients also interact with other parameters and with each other. And the reason for which I was able to do this study at the cost of only 57 high-fidelity simulations was because this problem has structure. And even though the given dimension was 8, the intrinsic dimension was 2. And we see that only a handful of parameters interact with each other, and these interactions are anisotropic. And basically, the total cost of this study was around 460,000 core hours, which is not necessarily very high. This is affordable for such a problem. Even more, because the approach is based on interpolation, it provides intrinsically an interpolation-based reduced model. And then we wanted to ascertain the accuracy of this reduced model. And to this end, we drew 32 random samples in the input domain, and then we evaluated both the high fidelity and the low fidelity models, and then we computed the mean squared error. And then here in this plot, you see the high fidelity result, so the heat flux versus the reduced model result. And then we see that most of them lie on this line, which means that actually the values predicted by the reduced model are very close to the ones predicted by the high fidelity model. And by computing the mean squared error, we got the mean squared error of the order of 10 to the negative 4, which is quite good. And also the reduced model, which is an interpolation-based reduced model, is very cheap, in the order of milliseconds to evaluate numerically. And this is about 9 orders of magnitude cheaper here. And what you also can see in this plot is that the values of the heat fluxes basically range from very small, in the order of close to 0, to very large, in the order of 2.8, 2.9 megawatt. And for this very wide range of heat fluxes, the reduced model actually did a fair job in approximating them. And here, I also zoomed in into two values, so one for a very small heat flux, one for a larger heat flux, to show you what exactly is computed here. And if you concentrate on these figures on the right in each zoomed in plot, the heat flux is a time varying quantity, and we are interested in the time average value. So basically, the high fidelity simulation goes into a transient regime, and then it reaches a quasi-steady state. And then what we do is we simply take the time average of that. And we see that the sparse read code produced a very accurate reconstruction. And we have not used the reduced model yet, but this can be used, for example, as a reduced model for this type of turbulence in different regions of the device, without the need to perform too many high fidelity simulations. So we want to use this reduced model also further and see whether it has extrapolation capabilities for these types of problems. So to summarize, sparse read approximations with dimension-adaptivity can be useful tools for doing UQ in realistic problems, because realistic problems with realistic models generally have structure, and we can exploit this structure with these methods. There are pros and cons of this type of approach. So one of them is that it is very easy to use. So very easy to couple, for example, even with a high performance computing code, because we just need access to the input parameters and the ability to compute the output of interest, and that's pretty much it. Generally, they tend to work well in practice, which is based on it's a heuristic. But at least for this approach that I presented here, we have no theoretical guarantees. So it's not really put on a solid theoretical foundation. And this is where, for example, some of the work that some of you in the room have done can come into help. And here I want to mention a few recent works from Diane and Fabio Nobile in the direction of adaptivity in stochastic Galerkin methods. And then some of the recent work of Jens Lang and Rob with David Sylvester on adaptive multi-level collocation, and then the recently published work of Martin Nigel and collaborators on convergence results for adaptivity in stochastic collocation. And even more potentially complementary methods to what I have presented could be, for example, multi-level or multi-fidelity methods, and especially multi-level for the type of code that I have used here, which is a grid-based code, or quasi-Monte Carlo sampling methods, because in general, what happens in these problems is that they tend to have structure, as I have said, and we can use this, for example, we can exploit this even further with the quasi-Monte Carlo sampling methods. And with that, I want to thank you for your attention.